Okay, decision trees. Remember I was talking about your boss yelling at you because your system doesn't work and you're like, I don't know, it's just numbers. Decision trees are beautiful because they're a learning method where at the end you get something called a decision tree. Do I have a picture of a decision tree? I don't think I do. Yeah, that's too bad. Decision tree is something where they actually have real decision trees. Like the folks over in like ecology and botany and stuff, like they make these things where like look at the leaf. Does it have little pointy parts or little round parts? And you're like, it's like you check out the tip. And here is the round branch, and here is the pointy branch. And then you go look at the veins, and you say, does it have branching vein structure? And then here, it's, branching. And then here, it's like, no. And then here, you say, does it have, I don't know what they do in botany, but, some other little feature of the leaf. Like, is it shiny? Does it have a waxy coating on it? Is it surface? The surface, is it waxy, or is it like matte? I'll call it. And then here it's like you've got a cactus, and then here it's like you've got a pine tree. At the end it classifies the thing for you. So at every step you're testing one feature of the input. Okay, whatever. I'm not a botanist, okay? Does it smell good when you scratch it? I don't know what they test, but it's a sticker. Yeah, it's a lollipop. So this is a decision, and you can just look at it and see what it's doing. It's like very intuitive. Like humans love this stuff. They'll eat it up. So if you're ever dealing with a human, you might want to give them a decision tree.
Here, read this.
So then the question is, okay, as computer scientists, someone presents us with a gob of training data that's like, here are the features of each training instance, and here was the correct label. We got to learn a decision tree. Okay, the hypothesis class is the space of all decision trees. And we have to search that space to find the best decision tree for the training data that we got.
Would you making it shorter?
Actually, we go the other way. There are lots of big decision trees, so you don't want to start there. There's only one degenerate decision tree. It's called a decision stump, actually, where you don't even test anything. You just say it's a pine tree. Because chances are, if you look around here, like it's going to be a pine tree, right? Have you looked around? It's like pine tree. So that's called the majority label. Is pine tree. So you start with a decision tree that's just a stump that just says pine tree, and then you look at all the places where you get it wrong, and you say, I better test whether it's got leaves or pine needles, and so that's your first branch. You build until you've gotten the data correct. It's very much like FOIL, the inductive logic programming algorithm, where you're elaborating your hypothesis until it correctly classifies all of the training data. Decision trees are great for data where the number of options for an attribute are discrete and small. Decision trees are not very awesome for real-valued data, because you're like, oh, let's branch on x1. Well, let's see. If it's 1.1, it's this. If it's 1.2, 1.3, 1.4, 1.5, all the way up to 500. Or, it's like not obvious how you branch on real-valued stuff. You can make it work. You can like try and find a threshold value or something, but it gets complicated, and it's just not the most natural use of decision trees. For this assignment, we actually give you heavily discretized data. So if you wanted to build a decision tree on it, you probably could. But I wouldn't recommend it. This is the example that they use in the book is kind of fun. It's Stuart Russell's brain. He's a very famous AI guy. He wrote your book. This is he willing to wait at the restaurant to get in? He lives in Berkeley, California. They have a lot of restaurants. does he know of an alternative restaurant where he could go? Can he wait at the bar of this restaurant? Is it a Friday? Is he hungry? How many patrons are at the restaurant? What's the price of the restaurant? Is it raining? Right? He may be more likely to wait and not go walking around somewhere else if it's raining outside. Does he have a reservation? If he has a reservation, then it's pretty likely they'd seat him soon, you'd think. What type of restaurant is it? And this is the estimated wait time. And then this is what he actually did. Like, he will wait? Yes. No. Like, he doesn't have a reservation. It's not raining. The restaurant's already full. It's Thai food. Maybe he's not big into Thai food, and he has an alternative that he could go to. And he's hungry, yeah. So he's not going to wait. The estimated wait time is over half an hour. He's out of there. So this is data on Stuart Russell's brain. So the question is, can we reverse engineer how Stuart Russell's brain works? Can we build the decision tree of his thoughts? So, trivial, right? Here's the data. Go. So you can see how hard it is for a computer. Like, I think humans, when confronted with this kind of data, would often kind of thrash around a bit, and they'd like latch on to things and not very systematic. But as computer scientists, we can start to be algorithmic about this. What we're going to do is this. This is how you build a decision tree. It's a recursive algorithm. This is why it requires 671. It's a prerequisite for this class. So here we are calling ourselves again. We're handed a bunch of training examples. The attributes that we have yet to branch on, because you're not allowed, in a decision tree, you're not allowed to branch on the same attribute twice. That doesn't make any sense. So these are the attributes you have not yet branched on. And this is the default label that you're going to use. So for example, this is probably the majority label for this. So if there are no examples left to test, then you just return the default label. Pretty straightforward. If all the examples have the same label, so the DT-learn function takes a bunch of examples and it returns a decision tree for them. So here we are returning the degenerate decision tree that's just a single label. It's like a decision stump or a decision twig, if you want. Decision leaf? I don't know. Anyway, it is a leaf node in the decision tree. I don't know what those things on pine needles are. Those are, I guess, a needle. I guess is what those are called. Pine tree, the little green things, pine tree needles. Yeah. So maybe these are needles, or maybe they're leaves. I don't know. So if there are no examples, we return the default. If they're all the same label, let's return that label, the one that they all have. Otherwise, figure out what the majority label is. If there are no more attributes left to branch on, then we return the majority label. So you'd come to this if we're going to call ourselves recursively, and if there's like lots of noise in the data or something, maybe we've already branched on every single label, but still all the examples that filter down to here, they're still heterogeneous. Then you just give the majority label. That's going to give the best classification accuracy. It's still going to get some wrong. Dan?
I mean, majority label isn't a parameter, so where does it come from again?
We figure it out. You look at the examples. These are the training examples, so they're all labeled. The no attributes of majority label. Otherwise, we have a heterogeneous set and we have some attributes to branch on. So we're going to build a decision tree. We're going to build a branching node. We're going to pick some attribute and branch on it. And this is the only complicated part. Well, first, how do you choose the attribute? And I'll talk about that in the next slide. And then at the branching node, so we remove A from the list of attributes, and then we go and we're going to construct the different branches. for every value v of a, we take just the examples that have that value for that attribute. And that's going to be the examples that have to be handled by that sub-branch of the decision tree. Right, very straightforward. Now we have our reduced attribute set, because we removed a from it. And m is was the majority label for all the attributes. So we just use it as the majority label for this subset, or the default label for the subset. And then, so we've added a branch at this node. We've added a branch for v. And then we're going to, after we've made all the different branches for all the different values, we return the node. Everybody get that? Pretty straightforward. So the question is just, how do we choose the attribute to branch on? What do you guys think? Frank?
I would split it up so it partitions stuff into as many different spots as possible.
Choose the attribute that splits things up so that they're the same number, there's equal a number of examples per value as possible. Why is it good to have balance in numbers? We're trying to maximize classification accuracy.
I guess that would be nicer for the depth of the tree.
It would make a smaller decision tree, but we're gonna shoot for accuracy here. Who has another idea?
I actually have a question.
Yeah, what's your question?
I was wondering about, I guess I'm confused by example with A equals B.
Yeah? So we're given a bunch of training examples. Every example is going to have a value for every attribute. So if we decided to branch on number of patrons, we'd have all those examples that had some, all those examples that had full, and all the examples that had none.
All right.
So that you'd have 3 different bunches if you happen to branch on that attribute. So this just means for every value, like, okay, v is equal to full. Take just the examples that have pat equal full, and then pass them down to this recursive call, and flesh out the decision tree along that branch. And when it comes back, that's going to be the subtree.
That makes sense. Cool.
Nathan?
Maybe you want to choose the action that splits.
Action, attribute. It says A.
It says A. I've been reading a lot of algorithms. Yeah, pick the attribute that splits the examples up into the most homogeneous sets.
Yes! Exactly. The attribute that reduces the uncertainty about the classification. So doesn't matter how balanced the examples are between the branches. You just want, if there's an attribute where if you test it, you classify everyone correctly, like all the examples that have pat equals some are will weight yes, and all the examples that have pat equal full is like will weight no, then by God, you should branch on pat. Exactly. So we want to choose the attribute so that when we look at the examples along the different branches, they're all the same label, or as close as possible to being the same label. Right? They have the purest mix of labels. Like they're all a single label. So how are we going to formalize that?
You're splitting off little options one at a time.
Well, we're gonna split things up so that we're building a little decision tree here, and if we decide to test on pat, and we've got the full and the sum and the none branches, whatever examples fall in here, I think we're trying to determine whether Stuart Russell is going to wait at the restaurant. So maybe if we go down here, all the ones that have pat equal full, maybe there were like 16 will weights and 2 won't weights. And here we've got, I guess it would be the other way around, wouldn't it? But you'd be more likely to not wait if it's full. Here, if there are no patrons in the restaurant, maybe that's actually a really bad sign, and you'd also not wait very much. Maybe there are 2 where you weighted and 8 where you didn't. And here, maybe there are 15 instances where you weighted and 0 where you didn't. So this has a fairly nicely skewed distribution at each leaf. Like there isn't that much uncertainty about the correct label for each of these.
So if it were like 7 and 8, that's a problem.
Yeah, if it were very balanced, that would be, as far as what the label was, that would be bad. Exactly. So that's what we need to formalize. And I'm going to use a very scary word to formalize it, but don't be scared. This is called entropy of a distribution. And that's how to compute it. And all I'm going to do is just show you that it makes sense. We're not going to try and derive this from first principles, but it makes a great Wikipedia entry. I would, if you're into this kind of thing, feel free to go look it up. For some reason, they use the letter H for entropy. I have no idea why. So entropy measures for a random variable how disordered the distribution is, and it's actually from information theory. It actually corresponds to the number of bits that you need in order to encode the distribution, in order to encode data that is distributed according to that distribution. Anyway, so you look for all the different values in the distribution. What's the probability of that value times the logarithm base 2 of the probability of getting that value. So, do I have an example on this slide? I think I don't. Yeah. Okay. Well, we'll just do one. This is going to be awful. All right. Let's see. Let me just write that down so I don't forget it. P of xi times log base 2 of p of xi. Okay. All right, we're going to go through this. You're going to suffer through this. It's not going to be suffering. It's going to be joyful. We're going to have 2 distributions. We're going to have one. These are going to be discrete probability distributions, and it's going to be a distribution over yes and no. And here's a distribution that's very well balanced. So you have a probability 0.5 of saying yes and a probability 0.5 of saying no. Here it's going to be very imbalanced. What's a nice... How about 0 for yes and 1 for no? Okay, so what are the entropies of these 2 distributions? Well, let's see here. Here, let's see, we've got negative, and then the probability of getting yes is 0.5. And I multiply that by the logarithm base 2 of 0.5. Anyone happen to remember what that is? Negative 1 times negative 1 plus, because I'm doing this summation, there's a chance of probability 0.5 of getting no. The log base 2 of 0.5 is also negative 1. So this whole thing is negative 1/2 plus negative 1/2, which the last time I checked, this is going to be negative 1, but then you take the negative, and so it's going to be 1. Here, let's see what we get for this distribution. What's the entropy of this distribution? How disordered is it? How much and this is fantastic. This is very cool. You need 1 bit to decide whether it's going to be yes or no, because it's completely uncertain. You have no guidance from the distribution itself. You need an entire bit to choose which answer you get. For here, let's choose. This is a very highly ordered distribution. Let's see what we have. So we have a 0% chance of getting a yes, so that's 0 times log base 2 of 0 is negative infinity, plus, now the probability of getting no is a 1 times the log base 2 of 1 is 0. Wow, look at that. So I've got 0 plus 0, which is a big fat 0.
Yeah, negative infinity.
0 times negative infinity is 0.
Yeah.
Undefined.
Anything times 0 is 0, dude. I don't care how big it is.
Any number times 0 is 0.
Anything times infinity.
That's so not true.
Um,
My 0 is bigger than your infinity. Anyway, so isn't that nice? You need 0 bits. You need 0 bits of information to encode this distribution because you always know the answer.
You sure you don't need negative infinity number of bits?
Yes. Entropy is between 0 and 1. We can do an intermediate example if you want. Do you want that? Should we do an intermediate?
You need half a bit.
Half a bit, exactly.
So
How does that work? Let's try and do an example. Let's see. It'd be great if we can pick numbers that have powers of 2 in them. Unless someone has a calculator. Okay, I guess we have a computer too we could use. Yes, no. So let's say you've got a 0.25 chance of saying yes. And I guess that leaves us with a 3/4 chance of saying no. So here we've got 1/4 times, so the log base 2 of 1/4, -2, plus 0.75 times, oh shit, Nathan's on it, log base 2 of 0.75. -0.45? Oh.
I think it's like negative
0.96. Okay.
Somebody can check that.
Okay. And now here we are. We've got 1/4 times -2 looks like -1/2. Plus, Nathan, can you help us out here? I know it's going to be a negative number that's like 0.73 or something. Let's go with 0.73. 0.72. Okay. So I guess I should change this into -0.5. And I'm supposed to subtract 0.72 from that. Oh, God. So this is negative... wait a minute. That's bigger than 1.
Yeah, log base 2.75 is negative 0.415.
I told somebody to check it.
I was doing it.
They don't bring it up.
Okay. Can you say it again?
Negative 0.415.
0.41. All right, thank you. So I multiply that by 0.75, and I'm getting something like -0.3, basically. So this is 0.8. So this is 0.8 bits. So you need 0.8 of a bit to encode a decision there. Yeah, that's decision theory or information theory for you. Yeah, and it's actually, there's a beautiful, this is, well, we'll come back to this when we talk about unsupervised learning, but this is a beautiful example how if you know a model of the phenomenon, you can do compression. Right? If I can perfectly predict what's coming over the channel, then you don't actually need to send me any data. If I have a pretty good idea what you're going to say, then I can compress what you've said enormously. By 0.2 of a bit, I guess. So 20% compression. Because I have a decent idea of what you're going to say. If I have no idea what you're going to say, then I need a full bit. So there's this like mathematical theory about communication. In fact, people have, one of the things, I can't remember if it was, I think it was Shannon himself, the guy who developed this theory, Claude Shannon, the same guy who invented Minimax, by the way. He also made a little robot mouse that solved mazes. Shannon computed the entropy of English, how many bits per word, he took English text and calculated the probability distribution for the next word at every point in the sentence. And I can't remember how many, I think they're like 4.3 bits per word in English. So like on average, people say like up to 16 different things in the next word. So when anyone ever asks you, oh, it was just so great. I mean, what can I say? You can say, well, there are actually 4.3 bits describing what you're about to say. That's slightly more than 16 and fewer than 32. So if you ever want to really annoy somebody, you can say that. Okay, so that's entropy. Everyone have a basic understanding of entropy? So we want to pick. So the entropy is a measure of how disordered. The entropy is a measure of how skewed the distribution is. So we want to choose. We're going to look for every attribute, for every possible attribute we could branch on in the decision tree, and we say, okay, I'm going to look for every attribute. What's the probability of a particular value? And what's the entropy of the distribution of labels in the examples that have that value for that attribute? All right, so we would like for these are x sub a is all the examples that have value a for this attribute a. And so if they're highly skewed, then this is going to have low entropy. This is going to be close to 0. And we want to weight that according to how many, what proportion of the examples have value A for that attribute. So this is a weighted sum of the entropies of all the branches that we would get if we branched on A. Okay? So you want this to be low. There's actually a quantity called information gain, which is take the entropy of all the examples and subtract off the entropy that you'd have if you had broken it up into groups according to A. And this is called the information gain after you branched on attribute A. And that's what we use to choose the attribute in a decision tree learner. So you want this is going to be constant for any attribute, and this is going to be lower for attributes that split into very pure subbranches. So therefore, high information gain is this constant minus a low number. So high information gain is good. Information gain? That's the only tricky part of decision tree learning is keeping track of this entropy stuff. And I do make people do this on exams. So just so you know. So that's decision trees. So that's a great learning method. You end up with an actual honest-to-God tree. Not everybody branches until you get perfection. Sometimes people stop when the information gain gets really small. Or you use cross-validation, of course. So this is called early stopping, because you don't want to overfit the data. If there's noise in your data, then there'll always be something good-looking to branch on, but it might actually be spurious. So you might want to stop early, or you might want to just use cross-validation to figure out a good threshold of information gain to stop at. So that's a decision tree.